session. Before you start your expert lecture, I would like to share a short biography of you on to the participants. Professor Rajeev Kumar Singh is an accomplished professional in the field of electrical engineering. He earned his BTech degree in electrical engineering from the College of Technology, Patnagar, India in 2001. Following that, he pursued his MTech degree in electrical machine and drives from IIT BHU, Varanasi, India in 2003. In 2013, he completed his PhD degree in electrical engineering from IIT Kanpur, India. Currently, Professor Singh holds the position of professor along with the head of department in the Department of Electrical Engineering at the IIT BHU Varanasi. His research interests primarily focus on renewable power conversion for hybrid microgrids, power conversion for electric vehicles or hybrid electric vehicles, optimal charging, discharging of energy storage systems, and converters modeling and control. Professor Singh's contribution to his research field are evident throughout his extensive publication. He has authored in more than 50 transaction or journal papers, one magazine, and 91 IEEE conference papers. His expertise extends to the project management as well. Professor Singh has successfully completed 6 sponsored projects, while an additional 6 projects are currently ongoing with him. He is actively involved in developing next generation low cost onboard technology to enhance the charging infrastructure for the electric vehicle in the country. Recognized for his dedication and achievements, Professor Singh was honored with the Shyama Varsne Benko 64 Best Educator Award by IIT BHU Varanasi in 2021. He also serves as Associate Editor IEEE Transaction on Industrial Electronics and Guest Editor in MDPI Energies. Professor Singh is leading a significant project that involves collaboration with the U.S. National Science Foundation and the Technology Innovation Hubs supported by India's Department of Science and Technology. Throughout his career, Professor Singh has received different notable accolades. He is also serving as the Secretary IEEE UP Section 2024 and the Chairman of IEEE Industry Application Society Chapter at IEEE VHU Varanasi from 2021. With this, I would request our expert Professor R.K. Singh sir to kindly enlighten us with his words of wisdom. Please, sir.
All right, thank you and good evening, everyone. Thanks for this wonderful introduction, Garima. Thanks to Dr. Mrinal Kanti Sarkar and Dr. Simanta, who happens to be my student. Perhaps due to some emergency, is not on this call today. So I'll share my screen and just let me know if everything is okay or not. Can you all see the slide on your screen?
Yes, sir.
So in today's talk, actually, just almost a few days back, I had another talk with the same team, and they had invited me to speak on electric vehicle and grid resiliency. In this today's talk, I'll be majorly focusing on the traction applications. Of course, it is also basically electric vehicle, right? But I will be touching upon the very relevant and pertinent traction application that is known as metro application. And as my area belongs to power electronics, I'll try to revolve the discussion around the power electronics. So, in metros, basically, if you closely look at the different functionality, you will find that it is nothing less than electric vehicle. So though we get confused with the electric vehicle that, okay, if it is electric vehicle, it is the vehicle that is running on the road. But there are vehicles that are running on the track as well. There are vehicles that are running on the air as well. So they are also considered as electric vehicle. Electric air buses are there. Electric aircrafts are being developed by the different national laboratories, CSIR laboratories, one of the laboratories, National Aerospace Laboratory that is developing two-seater electric aircraft. So they also fall under the electric aircraft or electric vehicle category. So what I thought of that, okay, since, in a short succession, I had to present two different sessions. So I thought of in this session, I will be mostly talking about the electric vehicle on the track, right? That is a traction application. So the overview would be that as I said that, what would be the power electronics component involved in the traction application? And I keep on always saying this fact that it is an era of power electronics, right? No matter what, any hardware level development is absolutely not possible without integrating power electronics into it. And electric vehicle or traction application also is not untouched with that. So power electronic transformer. So eventually what I will say that, okay, what should be the role of power electronics, and then in power electronics, what are the different components, right? And how in the power electronics or a power processor eventually are playing their role in the different functionalities of the traction application. Then of course, how can you integrate renewable with the traction devices, traction applications? And then I will touch upon some of the recent developments on the research work that we could able to carry out here at our place in IIT BHU Power Electronics Lab. So that would be the flow of my session. So just to start off the things, right? Let us try to visit the history of traction electrification. So the entire journey got started off in 1879, way back, right? And way back in 1879, the first electric railway basically was developed by Werner von Siemens for Berlin Industrial Exhibition. So he kind of developed one model for that, and it was a DC locomotive with 3 small wagons, and the output power was 2.2 kilowatt, and the voltage was 150. So this is a pictorial view of what basically Werner von Siemens has developed for the industrial exhibition way back in 1879 for the Germany, right? So that basically kicked off the entire development of the traction electrification. And then 2 years later, the electric street car basically came into existence by Siemens and Haas in Lichterfeld near Berlin, again in Germany. And they basically ran it for approximately 2.5 kilometer long line, and the output power was 7.8 kilowatt. So the journey started off way back in 1879. Then the railway traction got started off. Then the street car basically came into picture in after 2 years in 1881. So and this is the picture, basically very old picture that is there when the first prototype or first working model was developed. But when the question that basically arises is why at all train or metro is required, right? So the answer is it is a vital mode of transportation for goods and passenger, and it is the cheapest mode of transportation for goods and passengers, and they are least polluting of all transport, irrespective of the road or the air or the whatever mode of transport you consider. The traction mode of transport basically is the least polluted one. And India being one of the busiest urban transit hub in terms of commute volume, basically commuter volume between one place to other place, it becomes more pertinent for the country like us, and if you look at the Indian metro rail statistics. So this particular figure will give you the details of it, and you will find that okay, this is the daily ridership per kilometer, this one, and this is the daily ridership in per in lakhs. So in Delhi itself, you will find that almost 8,543 riders per kilometer are there in the metro. In Bangalore, it is even more. Mumbai, the number is even higher, right? 33,227 daily ridership per kilometer. And if you move along, you will find that the different number belonging to the Indian rail system, right? And if you just a minute, just hold on, right? Just hold on. Yeah, sorry. So, yeah. Now, is that okay? Am I audible? Can anyone confirm?
Yes, sir.
Yeah. So now this Nashik, these are some of the pics of the Nashik Neo Metro, Water Metro. Delhi Metro. So as I said that, people get confused that, okay, only with the, on the road basically is electric vehicle, but there is a water electric vehicle. There is a, neo electric vehicle. There is a, the track vehicle that is running on a track. So in general, what I can say is that, the trains and metros are, very vital mode of transportation, who can basically take the passengers and goods from one place to other. They are least polluting, and overall they are very cheap mode of transportation. And not only that, they are also, solution for the low carbon emission. As I said that if you look at this particular diagram, chart, you will find that, the flights, domestic flights, they basically emit 133 kilogram of, CO2. And long haul flights, basically they emit 102 gram of CO2. Passenger cars, 171, bus, 104. Right. But domestic rails, they do only 41 gram. The coaches, they only do for 27 gram of CO2 emissions. So this data has been taken from this source, right? So if eventually, what we can say that it also supports the low carbon emission, lower noise pollution, and you can have the mass transport capability, right? In one train itself, many of people can travel together. That is not possible, in the bulk transport is not possible with other modes of transport. And they have reduced road congestion. So if you compare with the road transport, the traction transport basically have reduced congestion. So these are some of the attractive features because of which, metros and others, these things have become popular. So if you now take a look at the growth of the metro trains in India, so eventually it got started off first with Calcutta, where they have built 3.4 kilometer underground metro network, right? And then first modern energy efficient AC metro came into existence with Delhi, the Delhi Metro Corporation. And they started off with only 8 kilometer of stretch, right? And if you look at the, hierarchical order of the development, you will find that before 2014, only 5 metros were there. And, in and after 2014, 13 basically have been added, and the current status is 18. And the commissioning of the new metro lines are also, ramping up. So you will find that, after 2014, 454 numbers are almost in the line to get it commissioned. Similarly, approved corridors, they have also increasing by 82. Metro passengers per day ridership is also increasing by 62. The current status is increasing. And if you compare the number of cities, so earlier in 2014, we had got only 5 cities, but by 2015, the plan of the government of India is to have 27 cities that would be having metro operation in their uh, transport system. Now, coming on to the traction system, basically that this metro has, and the power electronic component basically that are involved into it. So this is the first traction transformer that has been developed by ABB, and this is a traction control, the pictorial view of the traction control. But the point that I would like to bring up into your attention is that if you look at the different, devices that are responsible for carrying out the traction operation, so you will find that there would be 9 devices that will be playing their role, right from the traction transformer to the converter to the traction control. And the location of all these devices are very well, placed there in the diagram itself. So you can see that traction control and monitoring system, traction motor, diesel engine generator, auxiliary converter, battery charger, energy storage. So overall, overall, you will find that, the devices that are there, except this diesel engine generator, right? I mean, all these devices belong to the, electrical engineering. So either transformer, converter, control, monitoring system, traction motor, auxiliary converter, even battery charger also has got a lot of power electronics involved into it. And if you have got battery charger, you need to have the battery also, or the super capacitor also. So a lot of electrical part basically are playing their role in bringing up or in the development of the traction system. And the power electronics eventually is playing a lot of role into the entire, building process. And some of the key components, right? So because, all these things, I have been in one of the technical advisory committee of Delhi Metro Rail Corporation, constituted by Ministry of New and Renewable Energy. So I had actually taken a very detailed look at what are the different components. I have, went into the metro train, looked into all these specific, each and every component, how they work, what are their functionalities, what are their control mechanism, how remotely they are basically getting controlled and everything. So if you look at the, things on a high level, you will find that these are the overall, equipments, they are playing their role. So you will have the current collector, then you will start from auxiliary power supply, the correct current collector is there, then there would be a traction motor, there would be a propulsion inverter, driving gear, master controller, train control management system that will kind of, give you each and every detail of the acceleration, deceleration, and everything, and door operating equipment. And the whole idea that I would like to let you know is that, as I said that in the beginning, that the discussion would revolve around the power electronics. In every single unit, you will have the power electronics. If you need to collect the current, you need some sophisticated, power devices. Auxiliary power sources, they also have some power electronics involved. In order to drive the motor, you need a power electronic converter. Inverter also by itself is a power electronics. In the, door opening or train control management system, master controller. So hell of the power electronics are playing their role in the development of it. And if you overall categorize the, type of supplies that are there for the metro system, so you will find that eventually there are two types of supplies. One is the three-phase supplies, AC supply, another is a DC supply. They have got their respective advantages and disadvantages. So the advantages are that they are simple in configuration, maintenance is easy, and recent advancements led to the adoption of 25 kV AC system. But I would like to bring into your notice this particular data. So for up to 32,940 kilometers, so this basically traction has been developed, and this is the statistics that basically covers the details of all across the world, right? So up to 15 kilowatt to 15 kilovolt to 16 kilovolt and 2 to 3 hertz system is being used, and it is being used for these many kilometers of the traction, range, right? And 25 kilovolt, 50 hertz to 60 hertz system, 72,110 kilometer has already been laid down on the track, right? And other systems beyond that, less or other, that's more than or about 3,000 kilometers. So overall percentage, if you see, so from 15 to 25 kilovolt, so 51.2% basically overall system, the out of 100% proportion, 51.2% goes to this particular system, 15 kilovolt to 25 kilovolt, and 1.5% basically goes to this one, that is very less. And in India, this 25 kV system is being used in Delhi, Chennai, Jaipur, Hyderabad, and in Western countries, some of the countries like Seoul and Paris, they are using this 25 kV AC system. So there are DC system also. So they widely use 750 volt DC system. But there are, the other voltage levels also that basically are adopted. And if you look at this particular table, you will find that up to 1 kilovolt, 7,650 kilometers have already been laid down. from 1 to 2 kilovolt to 20,440 kilometers have been laid down, and over 2 kilovolt, 68,890. So if you sum up all these numbers, so finally you will come out to be, it will come out to be 96,980, and the total percentage is 47.3. So that means DC percentage is almost halfway through what AC percentage is, right? And some of the voltage ranges in older trams, they have been using 600 volt. Newer metros, they are using 750 volt system, DC system. For complex suburban lines, they are using 1500 volt line, and long distance geographical project, they are using 3 kilovolt line. So that is AC, DC, right? So eventually you will see that both basically, and the DC system basically are widely used in the Western countries, UK, New York, Singapore, Paris, Beijing, etc. Right, and Dubai. Some of the Indian cities like Kolkata and Bangalore, they have also started off using DC system. So both have got their advantages and disadvantages, but the opportunities basically that come out from the DC traction system is that you can get energy efficient system, right? More energy efficient system. The power density and energy consumption can be reduced through the DC system. And by increasing the voltage level, you can reduce the current level, and that's how the cross section of the cables basically get down, and you basically the aesthetics of the entire architecture becomes excellent. And because if your cross section of the cables gets reduced by increasing the voltage, that basically gives lot of flexibility in giving you a lot of space to develop a better aesthetic system, traction system in terms of the DC operation. So, and other opportunities, as I said, that you may have the high power density, you may have better energy efficiency, you may have energy regeneration system, energy consumption in terms of power electronic traction transformer, that I will be talking about it in the upcoming slides. So DC is picking up. What I mean to say is, because of the different advantages, high power density, high efficiency, regeneration system, and less energy consumption, better layout in the design because of the low cross section of the cables. So a lot of opportunities are there in order to put in our efforts as a techie or a researcher, where we can put in our concept to develop things with the DC traction system. Now, as I said that, some of the applications are that there would be energy distribution, right? And regenerative braking basically is something that becomes very important. I'll be talking in bit of a detail about it in after this one. So, but if you look at the application of the DC to DC converter in the railways, so you will find that in the auxiliary system, right? If you have got the engine driving control, braking system, indicators, warning, all those things, so they all basically are operated through DC power system. They are not operated with the AC power system, right? So in the cabin, in the auxiliary powering, in the regeneration, right, and in the energy distribution across the different cabin of the train, you will have DC to DC playing their role. And if you look at the entire consumption, right, so this is the complete 100% model. 40% goes to traction, 4% to drainage, 10% to lighting, 12% to elevator, 30% basically, and 30% goes to this aeration and air condition, and then 4% to others, means the transmission, all those the contingency things like door operation, this, that, everything, and the traction monitoring system. So this is all what the overall percentage of the consumption, right? And if you look at the losses, this particular diagram basically gives you losses also. So major losses basically occur in the braking operation, 17%. So, and if you can tap that one back, that basically gives you a lot of benefit and leverage to reutilize your energy, right? Because the 20% is there in the auxiliary, so that basically cannot be taken care of. But breaking 17 and percent and whatever losses is there during the electromagnetic and mechanical braking, if you can tap those energies, so 33% can be tapped and can be utilized back, right, in order to charge your battery or for powering the other devices. So that basically is a huge percentage where a lot of power electronics role basically come in. So now this is the new kind of technology, power electronic traction transformer. So they call it PETT, or also popularly known as traction transformer. So there is a lot of advantages that basically the solid state transformer offers in comparison with the line frequency conventional transformers. So those are the fundamental things that I'm not going to do. I cannot go into that detail because time is limited, and in the interest of the time, I need to cover the uh, peripheral research aspect of the technology. But if you look at, you will observe that it is nothing but a combination of converter along with the medium frequency transformer. So it has got different architectures, right? So what does this offer? This basically used to be very compact, and it gives you a very regulated operation at each and every node. So if this is, let's say, one of the power electronic traction transformer, so if AC to DC is employed here, you can regulate this part, you can regulate this part, and you can also regulate the motor part, right? So eventually, this offers basically few major advantages in terms of having better regulated operation at each stage, better efficiency, because the losses would be very less in comparison with the line frequency transformer. The weight and volume will come down significantly because you are using high frequency transformer here. Medium frequency means of the order of kilohertz or so, right? Tens of kilohertz. So this kind of concept has been widely accepted for the traction application, right? So and this basically this particular slide give you the comparative advantage of low frequency transformer to solid state transformer. So just have a look. The solid state transformer, weight and volume, cost, reliability, functionality, efficiency, everything basically is on a higher side or better than the low frequency transformer, because low frequency transformer does not give you a regulated operation. It just basically transfer power or energy from one port to other port. So having said that, this has become one of the very important tool in the development of the electric traction. And these are some of the topologies and architectures, the components, what you can say, of the power electronic traction transformer. So you will have the dual active bridge 4-quadrant, then you will have the MOSFETs, medium frequency transformers. You just look at this. So you will have AC to DC, so converters, then dual active bridge here, then inverter, and a medium frequency transformer. And of course, there would be, filtering operation. So this entire architecture eventually belongs to that, basically describes the solid state transformer or power electronic traction transformer. And nowadays, by the way, this has almost taken over the fundamental line frequency transformer, because the size basically gets reduced significantly, almost 1,000 times it gets reduced, because distribution transformer used to be huge in size. The core basically is the CRGO, and they are big and bulky in the nature. So having said that, the different architectures that are there with the solid state transformers are, cascaded H bridge converter, dual active bridge converter, and multi-level modular multi-level converter. So these are some of the developments in the field of traction transformer, or you can say power electronic traction transformer. So this one basically was developed way back in 1985, and you may see that how from AC to AC. So whole idea is that you have to convert AC into AC, and with the help of power electronic component and catenary that they are using is 15 kilovolt and 16.7 hertz, and this was developed way back in 1985. In 1993, This one is the single module front-end converter configuration, and this is the cascaded converter configuration that basically has the improved power rating, right? So likewise, if you move on, the power electronic traction transformers also have evolved with the time. So the early topologies, they were having more number of switches, the passive component, but with the time, the number of components, switches, other elements, kept on reducing, and eventually nowadays with very sophisticated and very, mm, good topologies have been developed where switches have also been optimized and other elements have also been optimized, right? So this topology is developed in 1996. This was developed in 1998, and you can see the modularity. So you may use many number of such modules in order to increase the power level and the voltage level, etc. And this was developed by ABB in 2002. In fact, that case we basically gave a thrust. So ABB have been very instrumental, not ABB and Alstom both. So they have been very instrumental in development of cascaded hybrid power electronic traction transformer. So this is 4.2 MVA rating, and it was working for the switching frequency of 10 kilohertz, right? And in 2003, Alstom basically has developed this particular configuration in which they are using, they have developed it for 15 kilovolt catenary, and the voltage rating was 1.5 MV. I mean, sorry, the transformer rating was 1.5 MVA, right? And the switching frequency was 5 kilohertz. So here the transformer was developed for 10 kilohertz. Here the transformer was developed for 5 kilohertz. So similarly, in 2007, Bombardier basically, they came up with this power electronic solid state transformer, and they have been using it in their traction devices, right? And in the different traction devices, traction metros and other applications. Similarly, in 2011, ABB again developed this particular module. So eventually, the journey kept on increasing, and we may say that the simplicity, the complexity was reduced, the number of elements kept on reducing. But some of the key challenges that have been there with the adoption of the power electronic traction transformer was that it has got very high initial cost, right? And initially, so many power electronic component, AC to DC, then again DC to DC, then back to AC. So at each stage, you need to involve a lot of power electronic component into it. So it was facing some designing difficulty and manufacturing difficulty, managing the electromagnetic interferences and all, then thermal management and cooling requirement, cooling technique. But these basically could have been overcome with the time, right? And subsequently, the future trends basically that came in this particular technology, that was basically with the use of wide bandgap devices, the size has been further reduced. Integration of the renewable basically made it more effective, and the converter topologies basically, as I said, that they came up with the state-of-the-art converter topologies that basically reduces the cost and improve the reliability, and also the control strategies have become simpler in comparison with the previous one. So having said that, one key feature that I would like to bring out here into the notice is the concept of this regenerative braking, right? So in fact, the key benefits are that you will get energy recovery, you will have reduced energy consumption, will not have mechanical braking, you will have electromagnetic braking. Efficiency will improve, fuel economy, lower greenhouse emission, because you are making use of the kinetic energy and getting it converted into electrical energy. So, so the way the flow basically with which it works, just have a look. It is traction wheel. Traction wheel, if you are putting the braking up system, the braking operation, then brake control would be there. That brake control basically will generate whatever kinetic energy will be fed to the inverter, and this particular inverter through basically power electronic interface will go to the battery and charge it. And again, if your battery is discharging, it will take power from the battery, and through inverter it will feed to the traction wheel. So that is how the entire loop basically is getting completed. And as I said, that in comparison with the conventional and regeneration, regenerative braking, you have got a lot of advantages. You have got the electromagnetic uh, operation. You will have the energy utilization back into the system. You will have better battery life, or you, by utilizing that energy, you use to charge the battery. Not only charge the battery, you can feed it back to the grid as well. So those are the benefits of the regenerative braking technique in comparison with the conventional technique. So, and the key components that basically gets involved into it. So if battery is discharging, that means it will be in the acceleration mode, and the flow will be something like this: the battery, inverter, motor, generator, and then the transmission, right? But when it is regenerating, right? So then what it would do, it will take it power back. It will go to the regenerating mode and then charge the battery, and there would be a power electronic involved into it, through which the entire power flow will take place, and charge the battery. And by the way, this is one example where you are charging the battery. With the regeneration, you can also, if the huge amount of power is generated in the metros, like in the Delhi Metro, Rail Corporation itself, if lot many metros are running together, so there are many metros basically that would be having under regeneration operation. So if, let's say, out of some 50, 30 are under regeneration, so they are producing huge amount of power, and the same power can be fed back to the grid. So that can also be utilized, right? So in a way, you are supporting the generation capacity of the utility grid as well. And then the entire flow, how takes place, if from station 1 to station 2, I mean, it would be kind of acceleration region, then the constant speed region, then the regenerative braking region, and that's how the entire, the flow of operation it takes place from one station to another station. And accordingly, the execution of the power electronics basically is kind of done. So this is something that I have already covered. Yeah, this is also, yeah, so in the acceleration, as I said, that the power will be taken from the battery to the inverter to the electric motor, and then it will go to the wheel. But in the braking operation, the other way is taking place. The braking will be happening here at this place, and then that will feed power back to this motor, to the inverter, and then it can charge the battery. So in a way, it is kind of having the power flow in another direction. So, so the status is what? If you look at the current status of the regenerative braking used in the traction application, so there are many modern traction, metros, basically modern metro systems. They are using this particular technique, like New York, London, and Tokyo. They have fully adopted regenerative braking. Even our Delhi Metro basically have adopted fully regenerative braking system. And this high-speed trains of some of the commuters rail. So not only in metros, in high-speed trains in Japan, basically this N700 series of Shinkansen in Japan, they have started using the regenerative braking concept from the 2009, right? And in Vande Bharat also. So Vande Bharat does not fall under the metro category; it is a normal rail. So they also have started using this regenerative braking concept. But some of the key challenges in implementing it is the infrastructure compatibility. If I say infrastructure compatibility, there is a point that needs discussion. So what happens? Supposing you have, unfortunately, in our country, still the manufacturing, industry is not at that level or a scale the way it is there in the Western countries. So because of that, what is happening? Let's say you have adapted the regenerative braking, and you have implemented some power electronic module into it. You have put it into the application and used some IGBT into it. After some 2 years of application, if that IGBT has gone faulty, So then you need to replace that IGBT, but due to supply chain issue, let's say Infineon says that now I'm not actually at all manufacturing that IC. So in order to replace, or get your processor fixed, even if there is a fault in one particular IGBT, you need to replace entire module, and that becomes very costly. That is what the infrastructural compatibility is. And that is a cruel reality, I can tell you. Because unless you will have the manufacturing units well established in the country itself that can say that, okay, if I have supplied you some module, I can take the warranty guarantee for next 10 years. Where anything is going wrong, I will have the stock available in my warehouse and I can get it repaired. So that is something that is the key issue in implementing as far as the India is concerned, and that is accounting for a huge cost consideration. Because for one simple IGBT, you have to replace the entire power module, and that basically is a huge burden as far as the cost is concerned. Now, this renewable and solar power also, they are playing a lot of role in the traction application, and even Delhi Metro Corporation, they are receiving 35% of the total power from solar PV, and they have got a plan to improve it to 50% by 2031, right? So, and these are some other details, like discoms are doing up to 65%, off-site solar power is 30%. So all those, so the whole idea is that, integrating solar power in the traction system can greatly reduce the carbon footprint and its dependency on the grid. So that is how, a lot of solar panels are being installed on the rooftop, on the depot, and the both sides are elevated corridors of the metro, right? So this integration will greatly reduce the carbon footprint. So with this background, very quickly, I will now let you know some of the developments that have taken place in our research lab, right? So we actually call it VL Perry. We have given it name, this Virtuous Lab of Power Electronics Research and Innovation. So in the traction application also, we have basically done, significant amount of work related to that. So if you look at this architecture, so this architecture shows that this basically is the DC powered metro, and this is the AC powered metro, right? So this is the DC bus bar and this is the AC bus bar. So we have kind of come up with the new converter control topology in order to kind of contribute into the power electronics development for the traction purpose itself. And these are some of the developments I have listed down, that we have come up with the new kind of dual active bridges, right? And modular AC to DC dual active bridges that will support to generate new and state-of-the-art power electronic interface. So one of the development basically is this. So with one of the PhD students, we have developed this power electronic interface where basically we have kind of almost simplified the control architecture. If I say simplified the control architecture, if you need to charge the battery, you need to have the constant current, constant voltage operation. But our proposed topology says that we don't need controller for that. You just change the switching frequency, run it for the resonant frequency, it will act as a current source. Run it half of the switching frequency, it will act as a voltage source, right? And that way you can get the constant current, constant voltage operation. And we got it patented also. We got it published in IEEE transactions. I mean, the concept has been published in IEEE transactions. So this is the developed prototype, picture, photograph. That's how it looks like. Very quickly, I will go through the results. So we have tested it for the dynamic, steady state, different kinds of, parameters, performance parameters have been verified for that. This perhaps I have already spoken in our previous, in my previous talk just almost few days back, where we could able to develop basically, but this is more related to the smart grid ecosystem. But subsequently, we found that the same can also be applied, because this is the dual active bridge. So same can also be applied on the traction application, where we get rid of the vulnerable electrolytic capacitor, and we could able to actually replace it with the better reliable film capacitor. So Other details, basically, I had already spoken of, so I'm not going to, further go into that details of it. So what we did, basically, we came up with the power electronic interface, and we utilized the capacitor, basically, of the converter itself as a DC link capacitor. So if you are building up a two-stage capacitor, you don't need to put up a lot of, electrolytic capacitor for bringing up a DC link. You can get it done with the low value of, capacitors as well. So we have tested it for different solar irradiance and everything, and we found out that, okay, things are working well. This is the full developed prototype, some, 1 kilowatt of hardware model that we developed. We could get the hardware result, as per our expectation. So this one is another one that basically has been developed with us, and this is, also, and then this one we have implemented here in the campus as well. So the beauty of it is this particular converter topology will actually take one input and can give you 3 simultaneous outputs, 1 AC and 2 DC. And in this solar power coach, this solar PV output voltage can act as an input to this converter. So it can be implemented here, and it can give you AC supply as well as DC supply. So this 19.5 volt DC can be utilized to charge your laptop, and 5 volt DC can be utilized to charge your mobile phone. So your dedicated power supplies are there. So you need not to put your adapters, exclusive adapter to charge your laptop or mobile phone battery. So that is a huge contribution, because you are getting rid of a lot of power electronics as far as the charging of these 2 batteries are there. And this is very well implemented. So we have implemented it in our campus, right? And 5 kilowatt model we have implemented, and it's working very nice. So these are some of the results pertaining to that power converter, right? So some steady state results and dynamic results. So this has also been published in IEEE transactions on power electronics. If anyone has got any interest to further, get to know about the details, he can go and get detailed information from that paper. So now I think, in the interest of the time, very quickly, in just next 5 minutes, I'll try to summarize. So this is another development, right? So this is solar PV based L2C2 hybrid converter. So this also can be put in place for this particular application, where you have got a solar PV on top of your metro, and then you put the power electronic interface, and that will generate AC and DC simultaneously. And the good part is that with the kind of power converter that we had developed, the leakage current was minimized. So there is no leakage current into it, and subsequently we could able to find that the smooth operation can be ensured, and the high step up operation, there are many USPs of this converter topologies. Like in hybrid converter topology, you have the constraint of modulation index duty ratio, some summation less than 1. So that we also have taken care of in this development. So this is what, and this is another development, AC to DC dual active bridge traction. In this, we have come up with a new kind of control algorithm. So that has reduced the switching of losses and the losses of the entire system by almost 66%, right? And it is directly converting from AC to DC dual active bridge. I mean, AC to DC. So some of the advantages of it is they have got high power density, and no electrolytic capacitor is taken here. Wide voltage range of operation, and it has got inherent soft switching for entire value, load range. And it can be utilized for unity power factor operation and power factor correction circuit. So this is the test bed, setup, photograph of it. And the results pertaining to this development, you can see the AC, DC, all parts are there. And we have also developed this multi-level inverter for traction power converter, where the features are that it has got 13 level, and the USP of this is it has got high power quality, higher voltage gain, the switching stresses and losses are reduced, and the That's how, the filter requirement has gone down because number of levels are more. So this is the setup that we have developed in the laboratory. These are the experimental results pertaining to that, and they all can be integrated with uh, the traction system. So in fact, we are in touch with DMRC, and we are also started conversation with RDSO Lucknow, and there we will be uh, providing them the intellectual kind of advices how to improve upon the whole traction power system by integrating power electronics into it, right? So these are some of the more results. So with this, now I'll come to the end of this particular session, and I'll be happy to take up the questions.
Good evening, sir. I am Dr. Vivek from BRCM College.
Yes, Vivek.
Question is that, sir, why only we have used the DC traction system in Bangalore and somewhere in Metro Railway in DMRC? Why not all places? What is the draw?
No. So that's what, say, Dr. Vivek, we need to understand the advantages and disadvantages of both the traction system, AC and DC. AC has got its own advantage that, all the devices, all the system, the transmission lines, they are already there. If you are to kind of go for the DC, you need to lay down the separate, lines and everything. But since now DC is coming up, and with the kind of devices and the loads we have, it has been observed that with the DC system, you can get better power density, and better energy efficiency, better reliability, energy regenerative braking system. So that is why, they have started off taking it or implementing it, you can say, as a kind of thing to start off, right? And once things goes well with the implementation, let's say they have implemented it and it has run successfully, right? Then it may be scaled up to the different corners of the country also.
Another question is that, sir, some have shown that before that it is DC to AC to DC converter, and again it is DC to AC converter. Now we have changed the transformer, we have used the AC to DC, then DC to DC, again DC to AC. So what are the benefits from that, sir?
Yeah, so at each stage you can get the regulated operation. Now if you, for this actually you need to understand the challenges associated with the conventional transformer. The conventional transformer, basically what happens, any disturbance happening at the input side will get transferred to the output side, because you don't have any mechanism to kind of filter it out in between, right? But if you have more stages in between, right? Let me kind of share my screen again. Perhaps that will, I'll take you to that particular point where this will be. Just a minute. So can you see this slide on your screen?
Yes, sir.
Yeah. So now supposing
Yes, sir.
the whole idea is to transfer power from this node to this node. But by having these many power electronic interfaces in between, you can, whatever disturbance is taking place at this node can be addressed by this power electronic interface, so that you can stabilize this DC link. So this will not be transferred even to the secondary of the transformer. Now, any disturbance that is taking place here can be regulated by this particular dual active bridge, and this can be made more stabilized, right? And subsequently, whatever problem is sag or swell or harmonic generation or whatever, I mean, a number of issues are there with the conventional system, that will not get transferred to this side, or if the problem is taking place at this side, it will not get transferred to that side. So you will get very smooth operation. And another thing is, this architecture says that, okay, let's say this is high voltage. So high voltage AC to high voltage DC. Now then high voltage DC to low voltage DC. Then in low voltage DC to low voltage AC. So implementation of this architecture becomes very easy in comparison with other architectures. There are other architectures also in for power electronic transformer, traction transformer. But the whole idea is that, it should not, you can have the reactive power balancing, you can have the harmonic, address, the disturbance taking place either at the input or output side will not be transmitted to another side. The harmonic content can be taken care of. So having more number of stages basically give you more degree of freedom, and that basically is one of the unique selling proposition of this solid state transformer.
Thank you, sir. Thank you. Thank you, sir.
Thank you, Dr. Vivek.
Dear participant, if you have more question, you can ask.
You may connect me offline also with my group if you have got, if you get some apprehension.
Meet you whenever I will get the chance. I am from Patna, but king in Haryana, sir.
Excellent.
Definitely.
Whenever you are traveling to Patna, you drop by to Varanasi
Yeah.
and come to our place.
It's my privilege, sir.
Yeah, please.
Okay. Thank you, sir. Thank you for your nice presentation, and you have accept our invitation within short notice of time. So thank you.
Thank you very
Sir,
much.
can I get your contact email ID? Email
Yeah,
ID.
I'm actually posting it on the chat box.
Okay, sir. Thank you, sir.
Just I'm posting it on the chat box. Yeah, so just now I posted it on the chat box.
Thank you, sir. Thank you, sir.
So there is a question by Kuldeep Singh, how much voltage level required for DC traction metro? So Kuldeep, actually many levels are there, 750, 1500, So I have already shown that in my slide that for earlier version 600 volts they got started off, and now they are going up to more than 3 kilovolt as well. All right, Doctor. I see 700 volt DC. Yes, yes. 700 volt DC is also there. Yeah, true. So all these ranges are there. I agree with you. Yes. All right, Dr. Minal. So if
Okay, sir. Thank you.
there is no further question, we may close the session.
Okay, sir. Thank you.
All right.
Thank you.
Thank you very much. Thank you.
So, dear participant, our next expert will join on 6:30. So please, 7:30. Sorry, 7:30. So you please be with us.
Thank you, Manal, sir. This is some other topic I have shown to.
Welcome, sir. Welcome.